Hi, this is a supplement for the Executive Black Belt class on multiple regression. And what we want to do in multiple regression is talk about a couple of things. Let's go to our chalkboard and kind of talk about this. So let's start out with sort of why multiple regression. Isn't simple regression complicated enough? And we'll also talk about sort of what it is. And then we'll talk about the mechanics of how to do it, the mechanics. And then we'll kind of talk about sort of the process of building a good multiple regression model. And yeah, we'll talk about the process of building a good multiple regression model. What I can tell you is that there are many, many, many ways and many, many, many techniques to do this because, quite frankly, in an empirical sense, least squares is pretty much the only or the major technique, I just put the major technique, that we have for fitting empirical data to curves. I mean, I guess we could use splines and things like that, cubic splines. But anyway, least squares regression is one of the big daddy techniques, and so I think as we go through and understand the why, the goal of really the last part right here is really just to give you a process, not the process. Okay, so that's what I want to talk about. Let's start out with, why multiple regression. Well, probably the main reason is that if we think about our processes, or we think about any attributes even of people or that we measure, like let's suppose we are measuring, one obvious example is if we are measuring intelligence, or maybe better yet, more concretely, IQ, right, which is a measure of something, whatever it is. People would argue that it doesn't measure intelligence, but it certainly measures something, and it's a hard measure. Well, there's lots of things that affect IQ, right? There's, like, we know that socioeconomic background changes how well you do on an IQ test, and we also know education level, and so forth. And there's lots of other things in there. There's other things that would be highly correlated with it, like SAT score, if you took the SAT, or maybe a score on the Regents math exam. Regents math exam is a New York State math exam. Now the point is that if we regressed IQ on any one of those, we might find that it was a bit blobbish, right? So certainly there are people who come from a low let's say socioeconomic background, or let's do education. Certainly there are people who have a high degree of education, or who have a low degree of education and have a high IQ. They're really smart, they just haven't been educated. And certainly the opposite can be true as well, highly educated people who are not all that smart. So the spread on that may look, in fact, something like this. And if we drew our best fit line, there's a lot of variation around there. And in fact, if we drew in the prediction intervals, it'd be pretty wide. So we couldn't just use education to predict IQ. You tell me your education level, and I'll tell you your IQ. We couldn't do that. However, we wouldn't want to discount it alone, right? So we might want to bolster that. I guess we would see the the in our model, remember in this case we're modeling y equals b0 plus b1x, or in this case we have IQ is equal to b0, some constant, whatever that constant is, right? It's where it crosses on this axis, that's b0 in this case. Plus, and let's just put EL times b1, right? I should have written it the other way. Let me erase that, and I'll write it the other way, in the other order, you see. Oh, my goodness, my eraser is leaving all sorts. This is just like a real chalkboard. It doesn't work all that well. Okay. There we go. Plus B1, again, another constant times education level. And we'll interpret that constant a little bit later. We might, if we fit that line, we might find something where the R squared was, say, approximately, I'm just making this up, but suppose the R squared were like 38%. Now, that's not that strong, but it's not something that we want to discount either. So we'd like to extend it. So that's why we want to do multiple regression. We want to add in these other variables into the model. So what does that actually look like? What does that look like? Well, instead of having a form that looks like this, y equals b0 plus b1x, we're simply going to add a bunch of new constants and a bunch of new x's into it. So we're going to extend it in multiple regression to y, again, single response or a single dependent variable, but we'll have multiple independent variables. b0 plus b1x, 1 plus b2 x2 plus b3 x3 plus ad infinitum, right? And we're hoping that by putting these other terms into the model, that our model will adjust to them and provide us with something where the R squared is expanded. Okay, so that's basically what multiple regression is. It's just instead of fitting a single line, I'm sorry, a line to a single variable, we're fitting multiple lines to multiple variables. Okay, now one bad thing is that we can't look at that picture so easily. It's not as easy to look at the picture. So instead, remember when we said we're going to look at the residuals to validate? And you may have been a bit confused before by that. Let me just kind of write out the process. One was we always plot something, right? We make a plot. Two, and I'll put a S at the end there. Two, we build, and this was looking at the p-values for the coefficients, but there was only one coefficient, so it was kind of confusing and silly. Now we're going to have more than one coefficient, one for each x. So we'll be able to see what's significant and what's not. We'll do a simple example and a more complex example. Number 3, and we looked at the R squared, remember that. Here we'll look at the R squared adjusted, which is similar to R squared, but it tells us a little bit about the power of adding each additional variable. And then 4, we validated, right? And this was just, we said looking at residual plots. And you may have noticed that in the beginning when we had an x and a y, and we had, like, let's say we had a weird pattern in our residuals, like some curved effect. Well, if we just made a plot, we'd be able to see that curved effect on the residuals. It just was, you know, changed the axis a little bit, made it more horizontal. This is the residual versus x, right? So instead of looking at y versus x, we're looking at the residual versus x, and it's just to the side. But now, since we can't really make this plot, we're going to have to rely on these residual plots a little bit more than we did before to make sure that there are patterns, and we'll see the predictive power changing as we add in additional variables. And of course, our prediction now will be from single x Okay? Simple as that. All right. One last thing that we want to talk about before we go on. We are talking about the situation where we have a y and many x's. Could be 1, could be 2, could be 3, could be 4, etc. But we're still confining ourselves to situations where this is a num and all of these are nums. Okay, we'll relax that later where we'll have some are cats. But right now, all of them are numerical variables. So if this is IQ score, this can't be a color of eyes, okay? But it could be economic level if we put a number on that, right? And it could be education level if we put a number on that, okay? And it could be SAT score, it's already a number, etc. All right? So let's do an example. And the example I want to do is actually taken from the book. It's an example that we covered a little bit earlier. It's people hours versus experience. Remember that one? Or versus service level. So if you recall, right, so we have we want to be able to predict service level, right? We'll be in a situation where we're providing a service to a customer, and we want to be able to provide a certain level of service. Okay, higher is better, and we want to see if we can predict the amount of people that we put into this process. See if that helps us predict what our service level is going to be. So let's check that out. Let's use Excel stats to do that. I think that you'll find that this works just fine to do that, and gives us a nice picture. So let's start out by doing our usual to_num. And actually, no, let's not. Let's just go directly to n_num. So here I've got 3. If you have two number variables, you go to to_num. If you have more than 2, you have to go to n_num. So n could be any, it could be 4, it could be 5, it could be 6. So the first thing it's going to do is it's going to come up with this dialog box that says number of variables to show on data sheet. It says 4. Now we only have 3, so why is it saying 4? Well, in linear regression, you have to make an extra estimate for the constant. Remember, it's B0 plus B1x1 plus B2x2 plus B3x3, etc. And so it likes to put that additional thing in there. Okay, here we'll also want to put in what the dependent variable is, because we know it. It's, in this case, service level. So let's go ahead and do that. There we have it right there. You can see it just makes sense. Here's the constant, so it creates a column for the constant, one for people hours and one for experience level, which is another piece of information that we're trying to fold in to see if we can make our regression better. So remember, the equation that we're looking for is y, woo, hello, invisible pen, y equals B0 plus B1x1 plus B2x2 here. That's what we're trying to fit. And we don't know the coefficients for B0, B1, and B2. So Excel stats we're going to use to help find out what those coefficients are. That's it. We're going to fit this equation. All right, so before we do, let's remind ourselves when we fit just this equation before, I crossed off a bit of the 1, we got none too stellar results. So let's just kind of remind ourselves of that. If you go to tab 2 here, it actually gives the regressions on a 1-by-1, so which is kind of nice. You know, there's the picture right there. You can see we got an R-squared of about 27%, which is not all that strong. Now, it did turn out significant. It did turn out to be a significant number when we looked at the p-value, but it wasn't all that strong, and so it's difficult to make predictions from that. Okay. Likewise, if we look at service level, whoops, not service level by service, experience, I mean, Experience also looks like there is a pretty reasonable correlation between these two variables. So, and in fact, the R-squared is higher. What if we could combine both of these to come up with an even better answer? So what we've done is, notice I've looked at the two scatter plots, always a very necessary thing. It looks like they're both somewhat correlated with service level. So let's throw them in the mix and let's see what we get. By going on the tab to multiple linear regression, we can see essentially Excel stats fit and what that equation is. Okay, so it predicts that our B0, go back to our pen, there it is, y equals B0 plus B1x plus B2x2. It says our B0, see this right here, this B0, that's 59. And it says our B1 is 0.43, and it says our B2 is 5. So what this means is that we can predict service level by starting from some default level, right? It's just sort of the default level. If I had no information, I'd just say, yeah, maybe it's 59. But if we added people, we know we're going to add, for every person that we add, or for every person hour that we add, we bump that estimate up by 0.43. So if we add 10 people hours, we bump that 59 up to, I guess, 63.3, which is 59 plus 4.3. And it also says plus 5 for every level unit of experience that we put in there, and I'm not exactly sure how that was measured, but experience level would be maybe the overall experience level in years of the group of the capacity that you were looking at. If we can increase that by 1, we get an additional boost of 5 on our service level. So again, by taking into account both of these, we can get a better prediction. That's the idea. Now let's see if that worked. Well, look at this. We went from, there's our R-squared right there, 75% now. So notice it's better than either one of them together. So by putting in both of these variables, we were able to achieve a higher R-squared than we could with either of them alone. Now the adjusted R-squared deals with a problem called collinearity, or if you want to sound highfalutin, you can call it multiple collinearity. It means the same thing. And that involves adding many terms, right? So we have an equation that just has 3 terms, an x1 and an x2. But what if we wanted to add an x3 or an x4 or an x5 or an x6? In our IQ example, we could easily see that once we started adding more terms, we're going to find things that are correlated with those other terms that we're adding. So we could probably think of things that we could add in, but they may be correlated with people hours or experience. And because of that, we won't get such a great bump from them. Maybe we'll only add a little bit. The adjusted R-squared helps us understand and gauge the incremental value that we get by adding additional terms into this. All right. Before we go ahead and use it for prediction, which is kind of what I want to do, right? I always want to do that. And I'm tempted to click on this button. But before we do, I'm going to go ahead and we'll look at building the model, and that's checking out these p-values here. So here it says, should we keep the constant? By default, we always do. Here's an interesting one. It says, should we even keep people hours in the model? And it's close. Remember, last time when we did it alone, it was extremely significant. But now that we've taken into account experience, it's no longer as significant. That happens a lot. It's borderline, so I'm tempted to keep it in. I tend to be a little bit more aggressive on these, so I tend to keep it if it's 0.1 or less, or 10% or less. Some people still stick with the p-value of 0.5 being low and let it go. I tend to use the 0.1. So let's leave it at that. I'm going to leave it in the model, and then this one certainly is significant. So our model will indeed be y equals 59. You know what? I'm just going to just erase this at this point. It really will be this model right here that I'm going to circle in red. Cross off, I'm not sure. I was trying to circle it. There we go. Service level is equal to 59 plus 0.43 times people hours plus 5 times experience. We're going to go with that. Okay? So let's take a look at the residuals before we go ahead and use it for prediction. And looking at the residuals versus predicted, or case number, it looks like I'm going to give this a 5-second rule. 5, 4, 3, 2, 1. I didn't see anything really pattern-wise sticking out. Maybe there's an outlier there or two, but not too much. So I'm going to mosey on by. And the residual patterns here look pretty darn good, actually. The normality looks good. There's our residual versus fitted. Again, I don't see any issues whatsoever with that. It looks like no patterns. So we're good to go. So let's go ahead and use it for prediction. And so, for example, what if we wanted to predict the service level? If we wanted to put in 15 people hours into this process instead of, say, 13, and but the experience level of this was 2.5 of those hours that we were putting in. You know, what would be our prediction? Let me lower the significant digits here so we can actually read it. There we go. So our service level, we would be predicting, here's the prediction interval right here, would be 78, right? 77, let me just remove the 2. There we go. Would be 78 plus or minus a few, and we'd say it's, but we're pretty confident, 95% confident, that's going to be between 71 and 85. Now that's a lot tighter than it was before. Okay, so let's see if we put in 10 people hours, but we had a higher experience level on that. What if we had an experience level of, say, 6? There it is, and we'd say that, yes, our service level is going to be quite a bit higher. In fact, we predict it's at least 84, all the way up to 102. In this case, 102 is a nonsense answer, right? 100 would be our max, so that's another thing to look out for. But it does, by playing with this model, it can give us an idea of what are the limits of what we need to put in. It can give us we can play what-if scenarios now with people hours and experience. Okay? So hopefully that was helpful, and it showed you that by adding experience in, we were able to get a lot more predictive power out of that. Okay. Let's close this down, and we'll close this down. We'll close this down. There we go. So that's our service level. Now I want to also do an example. Now the real question would be, what would happen if we had, instead of just 2 predictors, what if we had a bunch of predictors? And I want to take you through that example because there's a mindset in here where we're building a reasonable model as opposed to just any model, a kitchen sink model where we throw everything into the mix. And it'll give you an idea of what happens when you have many, many, many things, only some of which are important to keep in the model. Okay? So we'll talk about that in just a moment. Okay, so here I want to talk about what happens when, I want to continue that talk about what happens when we have many variables and we want to build a reasonable number. So a reasonable model that's based on a limited number of things. And we talked about this in the building regression models as using a concept known as Occam's razor. And that, again, simply states that given 2 models, if they both have equal predictive power, we should choose the simplest. So perhaps in in our model terms, if we're going to write out the model, there we go. If we're going to write out our model and we have 2 competing, say we have 2 competing models, y equals b0 plus b1x, and y equals b0, let's make it simple, plus b1 x1 plus b1 b2 x2, and they're both equal, and this is an important point. If they're both roughly equal in predictive power, then we should prefer to use this one. Okay? If they're both roughly equal, we should prefer to use this one. So now this was a simple case, but what if we had like 100? That actually happens nowadays when you can look at tons of data. So we're going to get out our machete and we're going to pare it all down and find solutions that are limited but still very powerful. And that's the idea, compact and still a lot of predictive power. All right, let me erase this and so we can go on. All right, so to do this, we're going to look at the Consumer Reports data from 1993. Sadly, we're going to look at highway miles per gallon and see what drives highway miles per gallon, which is in column H of the data. And why I said sadly is because as we look at this, we'll find that we haven't really improved a lot on that in the cars that are out today. It's basically still about the same. Sad. All right, so we're going to use this to build a predictive model for the autos. Okay, so let's go to it. So we're going to confine ourselves to the following predictors. When we open up the file, we'll see that there's many, many, many more things that we could use, but we're going to use engine size, horsepower, fuel capacity, length, width, rear seat room, and weight. So we're going to do that. Let me go to the file. Here's the file right here. You can see there's lots and lots and lots of things in here. But to use Excel stats num function, we're going to just select all of these. And you'll see, I think that this is going to be helpful. I'll just select columns H through Y. Select num. And I'll believe it that there's 19. And I'm going to say highway miles per gallon is my dependent variable. And there it is right there. And now all I'm going to do is take out the things that we're not going to use in the model. The airbag was a no, so I'll choose, whoops, I'll choose that as a no. I'm going to leave in the constant. Drivetrain was a no. Number of cylinders was no. Size, we're going to keep that in. Horsepower, yes. Revolutions per minute, no. Revolutions per minute, I guess there's two of them. Manual or non-manual, leave that in. Fuel capacity, yes. Passenger size, no. Length, yes. Wheelbase, no. Width, yes. U-turn, something, no. Rear seat room, yes. And weight. Oops, luggage, no. And weight. So there it is right there. We've got 1, 2, 3, 4, 5, 6, 7 variables in this. Complicated enough. Just to give you an idea, I'm going to click on the multiple regression. This is kitchen sink. This would look at all of them, and we can see that's a complex model, right? That's my y. It's equal to some constant plus b1x plus b2x plus b3x3 plus yada yada yada. We might be able to simplify that quite a bit by removing the terms that are not all that interesting to us, or not all that powerful, I should say. So let's go take a look. The first thing I want to do is I want to look at the scatter plots. Now, there's a shortcut, and you can look at something called a scatter plot matrix. I'm going to take out the constant for just a moment in order to do that. But it's still kind of a mess, and I think you'll see what I mean. When I click on this, what this does is it relates, it gives me scatter plots for all of the data versus others. So I'm just going to go very quickly through this, but it's kind of a mess, and you can see it takes a while to generate also. But by looking at this matrix, and you can see there's highway miles per gallon, engine size, horsepower, fuel capacity, and all that. So if I go to an intersection, like for example, this right here shows me highway miles per gallon versus engine size. Well, they may be correlated, but it's hard kind of for me to tell. This tells me engine size versus highway miles per gallon, so I may as well have just left this out because it's the same. It tells me more or less the same. So the only thing I can tell you about this is it does show me some things are correlated, but it also shows me that those correlation patterns look very similar for a few things. For example, engine size, horsepower, and fuel capacity all look and weight all look very similar. So maybe they're all kind of telling me the same thing, and I can eliminate some of the redundancy in my model. Now, you know, so I'm going to get rid of this for a moment, but you know that I'm not a big correlation guy, but we can look at the correlation matrix here, and if I get rid of some of those decimal points again, I'm not sure why they always give such huge numbers, but let's give 2. And if I look at this, I can scan through and find some fairly big correlations. There's a pretty big one. There's a pretty big one. And you know, these are not too bad either. There's a lot that are correlated with highway. Horsepower, engine size, you see. But look at that, fuel capacity is very highly correlated, as is weight. So we may expect some pretty significant terms in the model. Close down the correlation matrix. Now, to get a better idea of the scatter plots, I would suggest looking at them one at a time, because if you look at them one at a time, you can make sense of them. So here's, for example, highway miles per gallon versus engine size. And here it is versus horsepower. You can see they virtually look the same. And in fact, when we look at engine size versus horsepower, look at that. They're highly correlated. So if I add both of those in my model, I probably won't get much bang for my buck adding the second one once I've already got the first one in there. That's the idea that's going on. All right, so we're going to go ahead and go to it. So we're going to start with the full model. This is not the only way to do it, but we can start with the full model. And what I'm going to do is I'm going to go through and I'm going to look at those terms where what I would say are the least significant. So for example, right here, also going to see if I can take off a few more significant digits so we can read it better. Right here would be something that I would take off first. Okay, so in this case, I'm going to take off. I'm going to take out length. So I'm not sure why I got that. There we go. I'm going to take out length from my model. If I take out length, then I get a slightly different model that does not include length. See that? And now if I take out engine size, I have to go back to data, take out engine size, etc. And I'm simplifying this as I go ahead and do that. All right, so that's one way of doing it. Now, I'm not getting what was in the book, so let me take a moment here. Ah, I see what I did. I took out the constant to make the scatter plot, and I never put it back in. So I'm going to go ahead and put that back in so we have that. Here's that. I'll put all of them back in, engine size and length. And I think that's it. 1, 2, 3, 4, 5, 6, 7. Yes, that's 7. Now let's see if we get that. Yes, there's my constant, 23.158. Okay, all is well with the world. Got it. Okay. Okay, so got it. Okay, so what I'm going to do now is I'm going to, let's start by chopping some terms. So in this case, we have a large number of them that are not significant. We've got this one, this one, this one, and this one. They're all not significant, but we have to do them one by one because as we eliminate some of these terms, other things will become significant. So it's interesting that engine size isn't significant. It's probably because it's correlated with lots of other things. So let's see. Let's get rid of that one first and review. So we get rid of engine size. Take a look at that. And now it looks like horsepower would be the next one to go. And let's see, now it looks like yep, looks like rear seat is no longer no longer needed. And as we're watching this, you see that the R squared isn't changing all that much. If I'm going to add that rear seat back in. Oops. I'll add that rear seat back in. And we'll see that it went from 70 to 70. Basically, it didn't change at all. So we're going to be watching these guys right there as we do these changes, or we should be. So I get rid of that. There it is. See, it didn't change much at all. R squared is always going to change a little bit, but R squared adjusted, if it doesn't go significantly down, then we haven't removed any real predictive power from the model. Let's also remove width. You see now we've got stuff that's pretty significant in there. Let's remove width. And look at how much simpler our model is now. Now we only have to know a few things, and we did lose a tiny amount of predictive power, but essentially we went from 70% to 69.6. Not very much lost. So we can this might be a good starting point for the model. Now there's some other ways of doing this which might be more practical. So you may it may be easier to get certain measurements. Like, for example, if engine size were more important, were easier to get than, say, fuel capacity or length, you might want to look into what would happen if I swapped that and with fuel capacity, how much predictive power would I lose? And let's just take a look at that before we go on. And I'm just going to switch it with fuel capacity here. Engine size. Now we may lose a significant amount because that turned out to be not significant. Yeah, we lost a little bit, but it's interesting that there's lots of different variables that we can use here because they are mutually correlated. We go back to changing that to what it was, which was fuel capacity. And there we go. So there's our model that we're going to end up with. There's our regression equation, which, if you look at it, you'll recognize this as the one that is also on slide 92. So we ended up with a, let's erase that. We end up with a model that looks like y is equal to 39.12 plus 0.424 B1, I'm sorry, X1 plus 0.107 X2 plus 0.007 times X3, right, where X1 is fuel capacity, X2 is length, and X3 is weight. And that's basically it. So if we wanted to go ahead and make predictions from this, we could. Oops, except that I have forgotten something. What I've forgotten is I need to check those residuals. So the interesting thing is when I check the residuals look okay, but I do see a couple of outliers, right there and maybe right there. Now, if I know a little bit more about those, I might be able to answer some more basic questions. So, for example, this one, if I go to that series 1.42 and 39, so 42 and 39, if I look in my original data set, I can see if I can find those. It looks like it's the now it's the data set, right? So it would be this one, Geo, Prism, Geo Metro, and the Honda Civic. So these are extremely small things. They may be anomalous, so I may have a subcategory that I predict for those. And we'll talk about that when we do indicator variables. That could maybe help improve our regression even more. Okay, finally we can make some predictions. And if we wanted to, we could say, well, with a fuel capacity of X, whatever fuel capacity would be, say 5.5, and a length of 150, and a weight of 3,000 of 2,000, what would be our highway miles per gallon? We'd say it's roughly 38. We would predict, plus or minus whatever. So again, hopefully this makes a lot of sense to you. There's lots of different places in businesses where you'll want to predict using multiple predictors, anywhere from eHarmony, where we want to predict not just based on your education level, on a person's education level, but maybe also their geography, their latitude, their longitude, maybe their age, maybe their income level. And eHarmony, I think, says there's like 180 different factors in the model, and they spit out the perfect match for you, right? So that's what they're doing. They're using a regression equation when they do that. Netflix does the same thing to predict their inventory levels and to manage things. And Harrah's Casino does the same thing to predict how they can get the maximum amount of money from you as a gambler. How to make you not fail so quickly that you'll never come back. Okay, supposedly. All right, so that's it on multiple regression. So what we talked about in multiple regression was, first of all, why? Why do we need it? Well, sometimes just one predictor is not enough. We also talked about what it is. And remember, all it really is instead of predicting y equals b0 plus x plus b1 x1, we're adding other stuff into there, plus b2 x2 plus b3 x3, etc. We're adding more terms into the model, and we can ... that if we want. And then finally, we talked about the mechanics. Very similar, but it takes a little more time because you have more. So it's plot. It's the same. It's plot, build. Now this is a little more complicated, right? Because we have the p-value selection. R squared, right? Check adequacy, R squared. And then finally validate, which is a more important step here, which is the residuals. Now, if you want to do more advanced regression, residuals analysis can go a lot deeper. You saw a little bit about what I was doing at the end by looking at those single data points and looking for patterns and trying to ferret out additional variables that we might use to make adjustments. But that's for a different course. Just wanted to show you the mechanics of this. All right, well, I hope you found this illuminating and helpful, and we will see you soon.